All right. What we're trying to do in this first part of this course is we're trying to talk about derivatives and how things, the rate of change, how things change over time. But one of the first things we have to prove that the function is continuous, because all the theorems we're going to talk about, it says, assume that f of x is continuous over this closed interval or open interval. And that's what we're trying to do in this section, and the next section is prove continuity. We've been doing that sort of. But in this section, we're going to look at one-sided limits. What do you think a one-sided limit is, as the name entails? And what do you think it's used for? Why do you think it's important? Was that? No, it's just, well, it's good to prove continuity, help prove it. But remember that one example we had of this graph? That was one of our examples where we had what this is yes, we can find the area under the curve. We could find the limit points at each of these points. But the problem comes, what happens at the endpoints? Because if we're looking at one, this point here, does the limit exist? Yeah, it's somewhere up there. How do we know it exists? How do we know the limit is true? Because we have to approach one from both sides. Because that's a two-sided limit, because it has to go from both sides. But not all points will be that way. Can we find a two-sided limit at 2? No, because the function doesn't exist to the right. Can we find a limit here? No, because it doesn't exist on the left. So that's what this section is all about. Another example. Let's say our function is x over absolute value of x. As x approaches 0, does the limit exist? Remember, our limit as x approaches c of f of x equals some value L. This is the y value that's approaching. So does this work? Does this limit function work as x approaches 0 of this equation? Because the first thing you want to do is plug in 0. Does that work? No, we have 0 over 0. Unfortunately, we can't do too much with this equation. So we'll look at another way. What does the graph of it look like? See. So we can't use 0. So what happens when we come from the left? If we put negative values in there, negative 2 over absolute value of negative 2 is what? Negative 1. Negative 3 over absolute value of negative 3. Negative 1. And then same thing, negative 1 over absolute value of negative 1 is negative 1. So To the left of it, it approaches -1. How about from the right? 3 over absolute value of 3. And likewise with 2 and 1. But they're positive. So that's the graph of the function. It kind of looks like the stepwise function, the greatest integer function, except that at the integers, it doesn't jump up. So is it continuous? No. We say it's a jump discontinuity.
Is m zero? Because I see they're both open circles.
Well, it can't be, because there's no way this function here can ever be equal to anything. Because if you plug in 0, it's in 0 over 0.
Oh, okay.
It's a jump discontinuity. So it tells you that the limit of this function doesn't exist. But we see from the graphs, if we approach it from the left or from the right, we do have limit functions. The limits do exist. They're just not equal. So how do we represent that? Let's look at it from the left side. The limit as x approaches 0, since it's on the left-hand side, it's the negative side of our function. We saw that approaches -1. The left-sided limit. Sided limit.
For example, let's say it's on 3 instead of 0, would it still be negative if it's on the left side?
Yeah, this is not a negative per se. It simply means it's the left-hand side, because it all depends on, remember, our functions are always defined on, so far we're dealing with only closed intervals. And C is an element somewhere inside that interval. So what we're looking at here, we're looking at that side. So it's approaching C from the left-hand side. So that's how we would write x approaches C from the left. And A could be positive. And C, in this case, C is greater than A. What's that? It depends on what A and B is. Because if A and B are both positive integers, or numbers, then C has to be a positive number because it's in that domain. It simply means that I'm approaching C from the left. That's all it says. That just says left side of C. As you can guess, the other side, the one-sided right limit, looks like this. This is to the right side of C. And C is in that domain. Because it's coming to C from the right. Yeah, so it doesn't mean that the answer is positive, negative as a numbered line. It simply means right or left side. So now we can have values of limits. So the limit as x approaches 0 from the left of this is equal to what? -1. Because remember, it's coming to this side. And going to 0 from the right is going to be positive. Examples here. And remember, all numbers inside that interval are called interior points. Whenever we refer to interior points, we simply mean interior of that domain. So if our function we used to just talk about this. So what's the limit? 9. This is your C value. Plug it in there. So it's the limit of 3 squared. That equals 9. Well, let's look at it from the left and from the right. Still 9. This doesn't make it negative. It simply means I'm coming to 3 from the left side. I'm plugging in 0. I'm plugging in 1. I'm plugging in 2. The graph is still the same. It's still always going to be 9. So as I approach 3 from the left, that's what this is saying. I'm heading to 9 because all these values of our graph are getting closer and closer and closer to 9. Likewise, the right-sided, one-sided right limit of x squared is equal to also 9. That simply means I'm coming to 3 from the right, which means it's approaching 9.
Wouldn't you run the lines on the top of the graph, wouldn't it be under?
No, because if I'm approaching 3 from the right, this point is up here. This point is up here. I'm referring to the points on the graph. This x at 2 goes to there. Remember, that's when we had the epsilon delta proof. Given any, so we have a C value here that maps to an L value. So this is our C value in the domain. That's our limit. Here we have negative delta, positive delta. So this is C minus delta. This is C plus delta. And that corresponds to f of x minus epsilon, f of x plus epsilon. So it's just as this domain gets closer and closer and closer, these get closer and closer and closer to my final limit. That's what we're trying to say. And that's how we could tell if something is continuous or not. Let's see, where's my first example? There it is. Here's an example. the function f of x defined as 4 minus x squared on -2 and 2 is the one we just talked about. Can we find the limit at all interior points? Yeah, because if the limit, even if it's 1.9, we can find a limit because we can approach it from both sides. But now what happens at that function as I approach -2 from the left? What happens there? Can't be done. Because at -2, is there any graph on that side? No. So we cannot take a left side limit on that endpoint. Because it's a left endpoint, it only has values to the right. So we can only do that with -2. What this says is we can approach -2 from the right because each of these values are defined. And as we get closer to -2, where are these values going? What's happening here on the y-axis? They're going down to 0. And we do the same thing with the +2. We can only approach it from the left. And that's the same thing. It's approaching 0. All right, let's look at theorem 6. Let's start putting everything together. It says, suppose f of x, some function, is defined on an open interval containing C, except perhaps at C. F of x has a limit as x approaches C if and only if it has a left hand and right hand limit there. And they are equal. So here we're getting close to, suppose it's defined on the interval. That's one way of saying we're assuming that it's continuous. Because if it's this interval, that means every interior point of that interval has to exist. So what this is saying is the limit of the function as x approaches c exists, this exists and it equals some value L, if and only if, which is a biconditional. That's the if and only if. The limit as x approaches c from the left is equal to the limit as x approaches c from the right. And they both equal the same thing. Right. Yes, exactly. That's exactly what they're saying. Because if this one exists in the middle, that means it has to exist and they both have to point at the same thing, right? Which what?
It's just extending our function.
Pretty much. And this is how we're going to define continuity. Let's see. Let's look at example 2. Oops, yep. Like that? Yeah. It'll give me a chance to create this picture. So let's look what this means. We're going to look at x values, the two-sided limit, left-sided, right-sided. The one-sided left, one-sided right. So which points are we looking at? We're going to look at 0, at 1, 2, 3, and 4. But that's the domain of our graph. Our domain of our graph is from 0 to 4. So we have to look at all of these from 0, 1, 2, 3, and 4. At 0, does a two-sided limit exist? Remember, for a limit to exist, it has to exist on the domain. Is this value on the domain? Is negative in the domain? No. So it's true. It does exist on the domain. Because there are no right side. So this value is 1. Endpoints are the tricky ones. How about left side? Does not exist. Because you can't get to it from the left. How about the right side? Yeah, it approaches 1. Now, how about at 1? Do we have a two-sided limit? Does not exist. Why not? Yes, because there's a jump discontinuity. How about the one-sided left? Where's it going? To 0. How about to the right? To 1. You see, it doesn't exist because both the one-sided limits are going different directions, are different values. That's why it doesn't exist. How about at 2? Does the two-sided limit exist at 2? Well, let's see. Let's answer this one last. How about one-sided left? If we're coming to 2 from the left, what values is it approaching on the y values? It's approaching 1. Oop, 1. Because as I get closer to that value, it's always going to be 1. Same thing on this side. As I'm approaching 2 from the right-hand side, what was it approaching? It's approaching 1. Bless you. So does a two-sided exist? Yes, and it equals 1. Because if both of these are 1, this one has to be a 1. How about going to 3? Does the two-sided limit exist? What is the value? What is the one-sided left? One-sided right. Yeah, as we approach it from the right, all my y values are approaching 2. And how about 4? Does a two-sided exist? Well, it does because it's in the domain. The domain is from 0 to 4. There is no anything after that. So the value of the two-sided is 1. One-sided left, it's 1. One-sided right does not exist. So what this example showed us is the importance of defining the domain in which you're looking at. Since the domain is only from 0 to 4, this endpoint, I could only take it from this side. This endpoint is there, I can only take it. So that's why it has a two-sided existence. All right, let's look at the actual definition of a one-sided limit. One-sided limit. Okay, as you can see in your sheets. A. Assume the domain of our function contains or is contained in an interval. An open interval AB. No, not AB. It's CB. To the right of C. We say that the function f of x is a right-handed limit, and we'll call it L, at C. And we write it this way. Limit as x approaches C from the right of our function is equal to L. How do we know that's true and how it exists? We have to look at the epsilon delta proof. Remember the epsilon delta proof was f of x minus L is less than epsilon whenever X minus C is less than delta. So this is true. Except now at this end, we're no longer, since we're only on the interval CB, we have to be between there. Because this, our lower number is C and not 0. Well, it can be, but all depends what our domain is. If A and B are positive integers or negative and positive, then it depends on what those are. Likewise, the one-sided left, we just did right. The left limit or left-handed limit. It exists on an interval A comma C. To the left of C. Therefore, the limit as X approaches C from the left of our function is equal to L. And the proof of it is the absolute value of f of x minus L is less than epsilon when or if it goes C minus delta is less than absolute value of x minus C is less than C. Remember, the epsilon delta proof, we have to try to make this equation look like this. And then we compare the epsilon delta parts. And that's what we did last time.
Those, maybe, delta, right?
This one?
Right. Those here.
No, because C is the furthest right-hand point. That's what it says, to the left of C. So example 3. The limit as x approaches 0 from the right is equal to 0. Prove that. How do we prove it? Remember, it's to the right. So looking at what we just wrote, the way we prove it is by using this. So we got to use f of x minus L is less than epsilon. If this is true, it's C. So what do we put in there? What are our inputs? Well, what's this? That's our f of x. This is our c. This is our L. So now we got to put those all the way through there. So we have square root of x minus 0 0 got to be positive. Zero plus delta. So this gives us the absolute value of if 0 is less than absolute value of x is less than delta. Remember, we have to try to get the inside here to the same. So what do we have to do? We have to square it. So how are epsilon delta related? Delta equals epsilon squared. So what does that tell us? However close, however small that becomes, epsilon is even smaller. As x gets closer to c, our function gets much closer to the L. Remember, it doesn't have to get to it, it simply has to approach it infinitely close. Example 4. Show y equals there's no limit as x approaches 0, as you can see from the graph. What is this little squiggly? If you look at your picture in your graph, this is what the graph's supposed to look like. In other words, what's happening as it gets closer to 0? It's the period between them becomes infinitely close. So what does that tell us? Can you determine what the value is as it gets closer to 0? No. Since you can't determine whether it's positive 1 or negative 1, because those are the bounds, you can't, as x gets closer to 0, this function becomes undefined. Since you cannot, the limit doesn't exist because you can't determine whether it's 0 or 1. It's an oscillating function. Now, limits with sine x over x. This is going to appear with us for the rest of the next 2 or 3 semesters. What we're going to look at here is the limit of sine x over x as x approaches 0. What this graph looks like it looks like that. Why is there an open circle at 0? Because you can't divide by 0. But what is the limit as it approaches zero? So the limit of sine x over x or sine theta over theta, depending on what whether you use radian or degree measures, it always equals 1.
Is that the amplitude?
Well, it so happens it is the amplitude, but that's just what it equals. There's the example here. There, example 5. Show A, the limit as y approaches 0 of cosine y over y is 0, and B, the limit as x approaches 0 of cosine 2x over 5x equals 2 over 5. And you can't say, well, since sine y over y is 1, then cosine is the opposite, is 0. No, can't do that. So in this one, we have to use trigonometric identities. For cosine. A half angle of cosine y is equal to 1 minus 2 cosine squared y over 2. That's the half angle. So your angle. Right. So subtracting 1 from both sides, we have cosine y minus 1 equals negative 2 cosine squared y over 2. So now our equation we're looking at is the limit as y approaches 0 of cosine y minus 1. And that equals the limit as y approaches 0 of this side, negative 2 cosine squared y minus 2 divided by y. So this side is equal to this side. This negative, we take it out in front, the limit.
Put in the front of the limit?
Well, yes, since it's a constant, you can put it in front. Actually, you're supposed to put it in front. Now, using substitution, let theta equal y over 2. So we have negative the limit as y goes to 0 of cosine squared theta over theta. Oh, hold it, no. I'm sorry. This one should be sine. Because it's a half angle. So this one should be sine.
I also think you got your sines and cosines. So
That's. That was, so I don't know why I put cosine, but this cosine y equals 1 minus sine squared. So this is sine. So now this is going to be for theta going to 0. We can rewrite this one as sine theta times sine theta over y, or over theta. So we pair up these two, so we have sine theta over theta times sine theta. So what does this equal? It equals 1. So we have negative, this equals 1. And sine of theta as, because the limit, we did limit of both these, limit distributes to both of them, it's a product rule. So as, what's the sine of 0? So the answer is 0. And that's what we were trying to prove. The left side was proving that it equals 0. Now the other side. Everybody okay with this? Now the right-hand side, number 2. Oops, there. We're supposed to prove this equals this. Now we have coefficients in front of our variables. We have to get rid of those. If we multiply both the top and bottom by those actual coefficients, 205, what happens? What happens to the top? We simply have the limit of 2/5 cosine 2x this one says sine 2x. We have to try to make it prove that it equals 2/5. What happens on the bottom? The 5's cancel, so we have 2x. This is a coefficient, so it can go out in front. The limit as x approaches 0 of sine 2x over 2x. We let theta equals 2x. Then we get 2/5, the limit as theta approaches 0 of sine theta over theta. That equals 1, So the answer is 2/5. Yeah, so definitely have your trig identities available. And don't be like me. Make sure it's, if it says sine on the question, you put sine, not cosine. Is that what you meant earlier?
You're writing sine as cosine, I believe.
Sine of cosine?
No, like when you wrote sine, you wrote the cosine instead of the sine.
Yeah, I don't know why. I don't know, I don't know why I'm thinking of all cosines today. Again, calculus is simply the first step. Yep, the push the domino. The rest of it is algebra.
Recommend learning your trig identities or algebra?
Both. Because the identities are if you learn identities, that's just the beginning. Once you get the identities there, then it's all algebra. So everything boils down to algebra.
None of that work.
Algebra, it's Arabic. Al-Jabbar, that's where it's invented. In Al is from Jabra, is the region. Okay, find the limit of t as t goes to 0 of tangent t secant 2t over 3t. All right, let me pause this. All right, so the first thing we do, let's convert these into sine and cosine. This is sine t over cosine t times 1 over cosine 2t over 3t over 1. So we have a fraction over a fraction. Remember, whenever you have a fraction over a fraction, take the top fraction, leave it alone, flip the bottom, and multiply them together. So the limit as t approaches 0 of sine t times 1 cosine t times cosine 2t times the flip of this one, 1 over 3t. This is one long equation, so it's multiplied. We actually have 4 parts here. We have 4 parts. This constant, I could put it out in front, so it's 1 over 3. This sine t, I could pair it up with t. Because of commutativity and associativity, I could put them up there however I want to. This is 1 over cosine 1 over cosine 2t. Any questions so far? Did everybody see what I just did? It's just a matter of mixing, like I don't know if you remember Garanimals. You can mix and match clothes by those little tags. So 1/3 is a coefficient, a constant, so it goes out in front. The limit t goes to 0. Sine t over t. 1 over cosine t 1 over cosine 2t. We can just plug in 0 right now. What is sine t over t become? 1. Remember, the limit of sine t over t as t goes to 0 is 1. What is cosine of 0? 1. So it's 1 over 1 is 1. 2 times 0 is 0. Cosine of 0 is 1. So 1 times 1, so that all of this becomes 1. So we're left with 1/3. You were close though. I'm not gonna lie to you. What you all were probably doing is making it more difficult than it was. So what path did y'all take? What were you working on? What were you trying to do? What's that?
Get rid of the sign.
Well, yeah, but we couldn't. Once we convert tangent and secant into sine and cosine, fortunately, they have cosine on the bottom. That's a good sign that we're looking for. Since the cosines are on the denominator, I could go ahead and plug in that. There's 0 over 3, but I can simplify even further. And this is how we do it. So if you have trig functions, always break them down to the sine and cosine. That makes it much easier at the basic level. Now we're going to use the last example.
So when you use the example of the last class, example 5.
Oh yeah, yeah. Are non-zero constants. How far do we get in that one? Well, I'll say I'll just create that one and I'll send it to everybody. Because it'll be, oh yeah, because that one is very labor intensive. That's my head was hurting when I was looking at it. Okay, here's our equation. The limit of theta as theta goes to 0 of sine A theta over sine B theta equals A over B. Actually, and this example also shows us that anytime you have sine this, it's just the coefficients of your angle.
The sign over sign is 1.
Yes, but you can't do it that way because A and B are different. So it's like sine of pi over 2 and sine 3 pi over 2 or whatever, something like that. So they don't have to be the same. So let's look at this. My approach is here is I have sine A theta over sine B theta. Unlike the last example, remember we had sine 2 theta over 5 or 2t over 5t, where we had to treat them both separately. Now, since both A and B are part of the angle itself, we have to look at how both of those work. So what we have to do here is we'll have to get rid of the A theta. And the same with the B. We're multiplying by 1. The reason we're doing this is because, remember, we want sine x over x. So I'm just changing the way it looks. So here I have sine A theta. I want to multiply it to this one. A theta over A theta times 1 over sine B theta times B theta over B theta. Remember, these are multiplied. So I can take this one and put it under here. So I have sine A theta over A theta times A theta and I'll move this one, B theta over sine B theta times 1 over B theta. I have sine A theta over A theta times 1 over R. B theta over sine B theta times A theta over B theta. By commutativity, I can move them all around. I can associate them how I want to. Since they're all multiplied, it doesn't matter. So as theta goes to 0, what does this equal? 1. And this one? Also 1, because it's the same as 1 over that. So this is also 1. And here, the thetas cancel. So what are we left with? And that's that. Yeah, I'm glad you asked the question. Which one should we? Yeah, you have to know both. The trig identities, but use I have online all the formulas, use those. Who has not printed those out yet? Okay, if you want me to, I can print them out, use their ink. Okay, I'll just bring a set for everybody, so we use them in class. Yeah, it makes, and we'll need those as we go along, because we're gonna be using a lot of identities. Yes,
Can I couple the laptop make sense?
what's that?
Can I have a laptop will make sense?
Yeah, sure. Yeah, of course. Okay, that does it for that section.